Yep, we're recording. I didn't know we were recording already. Fair enough. Okay. Well, good morning, everybody. Hello. I hope you're doing well. This is our quick notes on combination circuits and an explanation using the first one from your packet. So if you're following along there, this is the circuit that is combination circuit number 1. But to help understand combination circuits, I want to reference this drawing I made over here. I have titled the Physics Fountain of Knowledge. Because it turns out the rules of a combination circuit are the same rules for a series circuit and a parallel circuit, just combined. So let's take a look real quick at what we mean. Here in a fountain, you have a base pool at the bottom, and some kind of pump and a pipe sucks the water up to put it out at the top. So you can think of the pump like the battery of a circuit. It's going to raise you to your full potential in order to flow through the circuit. Here we have a stream of water coming out into this top basin that only has one opening for the fountain. The openings are like our resistors. So the current going through this one opening has to match the current coming in. That's the rule in series. In our circuit over here, we see that the current going through the battery would have to match the current through resistor 3. They're in series with each other. That is a single line. So current flowing in matches current coming out for anything that's on a single line. Current is same. Now, as we drop down into the second basin, we see we have two openings here. These two openings are like resistors in parallel. And I purposefully drew one opening a lot wider than the other. That wider opening would allow more current to flow. This opening would have less flow. But those currents through each, current through R1 and current through R2, would have to add up to the total current coming back out from the junction or coming into the junction. Either way you want to look at it, either what's getting sucked out or what's pouring in, those two openings have to add up. That's a parallel rule, and those resistors are in parallel. So we say current adds up. I hope so far so good you're following along fairly well. I'm going to switch thought processes now. We want to talk next about voltage. And then we're going to look at actually solving this, and we'll talk about resistance there. For voltage, we said the pipe was equal to the initial voltage, that whole combined piece. But what we see here is we get a drop. We get some amount of reduction in energy. So we have this one piece right here, which is R3, that has some amount of voltage. We'll call it V3. Some amount of loss from the beginning. Then we have a second drop over here where these other two pieces are at the same height. This piece to the bottom and this piece to the bottom is the same fall. So the voltage drop for R1 and R2, it really doesn't matter which one. Ooh, that's an R. I need a V. We're going to call it V12. It's the voltage drop no matter which path you take. So there's a little bit of drop here. Doesn't matter if I went through number 1 or if I went through number 2. It's the same amount. And there's a different drop here. And what we remember in series is drop plus drop equals the total of the pump. In other words, for this circuit, the total voltage at the battery has to equal the drop right here at resistor 3 plus the drop at resistor 1 or resistor 2, because they are in parallel. It doesn't matter which path you take. The biggest change from our parallel rule was in parallel, we said it added up to the battery. In combination, they are equal, but there's other pieces to add to it. Just like in our fountain, there was a piece here that took away from the pipe and a piece here that took away from the pipe. So with all that in mind, let's solve. You can always rewind, restart, however you want to do it, go back and look at my analogies with the fountain. I hope they help. But for solving, guys, we're still going to use the Veer table. It's a nice organizational tool to help you keep up with everything you're doing. There we go. Mostly pretty. All right, I'm going to write in my knowns. I know the voltage at the battery, that's my total voltage, was 30 volts. I know resistor 1 is 24, resistor 2 is 12, and resistor 3 is 2. And the other thing I want to make sure that we note is that it's resistors 1 and 2 that I follow with the parallel rules, and resistor 3 and the battery follow the series rules. So the Veer table is great, and it's still V equals I times R. But we want to remember that part of this table is now parallel, part of it is series, so I have to be careful with my rules. Let's take a look at how that plays out. First and foremost, guys, I want to get the total resistance. That total resistance, I've got to add 2 of them in parallel. Let's see, parallel was 1 over the total equals 1 over R1 plus 1 over R2. Just barely enough room over there, huh? Let's shift slightly for you. So let's see, R1 we said was 24 and R2 was 12. You can use your calculator, but these are nice numbers. I can get a common denominator. 1 over the total is 1 over 24 plus 2 over 24. Because 2 times 1 is 2 and 2 times 12 is 24. Like denominators mean I can add the numerator, or 3 over 24. Cross multiply, 3RT equals 24 times 1. And 24 divided by 3 is 8 ohms. 8 ohms. So what I'm really saying here, guys, is I could, let me get rid of all these crazy notes. I could rip these 2 resistors out, and I could replace both of them with a single resistance of 8 ohms. That's the parallel piece combined. Well, now I have series, an 8 and a 2 and a total. And we said resistance in series just adds up, or 8 from the parallel piece plus the 2 at R3 is a total of 10 ohms. So it's a little more complex because it is a complex circuit, but we use both of our rules in turn and we get to the end number. Now here's the good news. That is as far as I would take you on a test or a quiz. I'm going to just ask you about resistors. For the purposes of the circus, it's fun to review other pieces. So real quick, 30 V equals something times 10. Do you know what times 10 is 30? I hope you know that's 3. And I just erased it, but we said 3 was the same in series. And 3 and the total are the same. Just like on our fountain, the current coming out of the pipe was equal to the current flowing through that one opening in series. So that's kind of nice. Oh, I can do 3 times 2 also. That's not too bad. 3 times 2 is 6 volts for my voltage. And then here's the one part I think gets a little bit of confusion. In parallel, the voltages have to be the same, but in series, they have to add up. So what I need here is a number that the total voltage is equal to 6 plus something. And that something will be the number in both, because in the fountain, it didn't matter which drop I went through. But I need to know at how high that opening is. Well, if you subtract 6, we find out that missing blank right there is actually 24 volts. You don't split it in half because there's 2 resistors. It's 24 to fall through here, or 24 to fall through there. And then finally, what about those missing currents? Well, something times 24 has to equal 24. Hopefully you know that's 1. Something times 12 equals 24. A little more challenging, but 2. And then final self-check. We said the current plus the current equaled the total is 1 plus 2, 3 amps. You bet it is. So that's solving a combination circuit. Kind of like a fountain falling through the water sources, we can solve everything in our complex circuits. If you're not sure where to go, remember the blanks that are on the page with your combination circuits are in order. So you're able to see what the next question is to give you a hint of where to be solving. As always, if you have questions, feel free to ask in Zoom. We can type, we can chat, whatever you need to do. Odds are good other people are having the same question, so feel free to ask it out loud. Have a great day, and I'll see you in class.